So how do we figure out the bond energy of this system? What are we going to need to do there?
For this problem, since it's asking us to only count the contribution from...
Sorry, what was that?
Can you hear me?
Barely. Can you speak any louder?
Is this better?
Yeah, thanks.
Cool. So for this problem, since it's asking us to do the contribution of nearest neighbor bonds, you would do the -1/2 number nearest neighbors bonds times Avogadro's number times number of moles times epsilon. And they give us epsilon.
Yeah, I think that should work.
Yeah, and then they give us epsilon as 1.15 times 10 to the -22, and we should know the rest of the numbers, and we just plug and chug.
Right. So we got number of bonds times, and how many particles are we actually dealing with here?
2 moles, so Avogadro's number times 2.
Yeah. And so we've got number of bonds. I'm just going to write the epsilon as epsilon for now. We can fill in the value afterwards. Number of bonds. How many bonds per particle can we expect here? We just take a look at one particle. How many neighbors does it have?
6.
Yeah, looks like that one particle has 6 nearest neighbors. Because we got, if we just list them, we got 1, 2, 3, 4, 5, 6 nearest neighbors. So that's definitely 6. And then number of particles, 2 times Avogadro's number. And does this double count? Do we need to divide by 2 to eliminate double counting?
Yes.
Yeah, and we can always check by looking at another nearby particle. Like if we also say this atom has 6 nearest neighbors, and we actually mark those, 1, 2, 3, 4, 5, 6, we've just counted this bond twice. And if we keep this going, if we say every bond has, or every particle has 6 bonds, we'll be counting every bond twice. So yes, we do need to divide by 2 to eliminate double counting. 6 times 2 over 2 just becomes 6. So -6 times epsilon times Avogadro's number should give us the value we need here. And that will be -6 times epsilon, in this case, is 1.15 times 10 to the -22 joules. Avogadro's number is 6.02 times 10 to the +23. So 10 to the -22 and 10 to the +23 just become 10. Then 6 times 6 times 1.15 is going to be about 40-ish. See if I can get something a little more precise. 6 times 6.02 times 1.15, about 41.5. So 41.5 times 10 to the 1 joules, or 415 joules. Oh, I forgot the negative. -415 joules.
I have a slightly unrelated question, but say you were asked to include next to nearest neighbors in your calculation. There were problems like this, and they said that the RO for next to nearest neighbors in this case would be √3 times RO, and I'm a bit confused as to where they're getting the √3 from.
Well, let's take a look at those nearest neighbors and see if we can find them. Using, let's say, the same center of particle. If we want more accuracy, if we want to find the second nearest neighbors, let's draw out lines from there to the next nearest neighbors. Like, for instance, from this central atom, which direction could you go to find the next nearest neighbor, the particle just a little bit further away?
You could go in between and like all the way up.
If you go in between those, this is the second nearest neighbor because it's just a little bit further out. And I find it's often useful to visualize this in terms of circles. Like all the particles that are the same distance away are going to form a circle around that center atom, because a circle is literally just the set of all points equidistant from a central point. if you imagine this circle expanding outwards from the center, the first particles it hits are all of the nearest neighbors. And then if you expand that circle further outwards, the next particles it hits are all of the second nearest neighbors. So those would be something like these ones. And it's difficult to make sure this is exactly centered, but notice that those 6 particles all appear to be equidistant from the center. Mm-hmm. And the other ones, like for instance, this one here, if we were to draw out a line to this one, that's a little bit further. That goes beyond that circle. Yeah. So that would actually be a third nearest neighbor. Okay. But the second nearest neighbors, we'd be going through these between the nearest neighbors passages. Those would be the second nearest neighbors.
Okay.
Looks like we have how many of those?
6.
Yeah, we got 6 copies of those. So if we wanted to figure out the energy of all of the second nearest neighbors, we could use the same general sort of formula. We just have to modify it. We've got negative, and it's not going to be epsilon in this case because those bonds are weaker. It's going to be negative some fraction times epsilon.
How would you find that fraction in this case, though? That's
where I'm getting fraction. Yeah, we're going to need to know a distance, right? Because if we know a distance, we can just look up the energy on the Lennard-Jones potential graph. The rest of it we can fill in. Yeah, go ahead.
In this case, since it's a circle and it's looking like our main atom is right in the center, would you find the radius of the circle?
Yeah, which is really just that distance from the central atom to one of the other atoms of interest.
Okay.
The circle itself, I think, is not going to be particularly helpful because the only formula that would really be relevant for the circle is circumference equals 2 pi r, but we don't know the circumference either.
Yeah.
What we could do, though, it's often useful to start looking for triangles. For example, if we have, let me clear some of this so we can focus on just one of those sides. Let's say this side length here.
Mm-hmm.
That side length is what we're trying to find. But we also know that this distance is a nearest neighbor distance. That's just R naught. So we know that distance anyway. And is there any other distance we know that we can use to complete a triangle here, specifically a right triangle?
If you use the distance between so there's that point that the green line connects to and the point that the pink line connects to. If you connect those two, it's 2RL.
Yeah, that's just 2 copies of R naught. So we can write in 2 R naught there, 2 times R naught. And that gives us 2 of the 3 sides of a right triangle. So we should be able to use the Pythagorean theorem here.
Okay.
If we let's say we call this missing side just distance D. Then we can set up our usual Pythagorean theorem. We just say side length D squared plus side length R naught squared equals side length 2 R naught squared, the hypotenuse. And how would we solve that for D here?
It would be 4 R naught squared minus R naught squared square root.
Yeah, we get 3 times R naught squared, and then take the square root of both sides. D squared becomes just D. 3 and we can split up square roots over multiplication like this. So that's going to be square root of 3 times square root of R naught squared, which is just R naught. So that distance D is going to be root 3 times R naught. Any questions on that so far?
Thank you so much.
Mm-hmm. Also, what's R naught in terms of this graph? Because this graph is marked in sigma, right? What's R naught?
Or what's our usual? Sorry, is it 1.12 sigma?
Yeah, we generally assume that R naught is about 1.12 times sigma. R naught is approximately 1.12 sigma. If you're asked to find distance, the process for distance is going to vary depending on the geometry, but the Pythagorean theorem is usually a good place to start. So whatever distance you're trying to find, mark that on the diagram as just a line segment labeled with a variable. Look for other line segments whose distances you know, usually R naught or some multiples of R naught, or other distances you've already calculated. And try forming something like a right triangle. As long as you can form a right triangle with all of the sides known except for one, then you can use the Pythagorean theorem on that. Or alternatively, maybe you only know one of the sides, but you also know one of the non-right angles. Then you can use right triangle trigonometry, sine, cosine, tangent, to find the missing sides. So it is going to vary from situation to situation. It really depends on the geometry of the situation, but often the Pythagorean theorem is a good place to start with, as long as you can establish some sort of right triangle. So filling that in, square root of 3 times 1.12 sigma, because we can replace R naught with 1.12 sigma. So square root of 3 times 1.12, 3 times 1.12 is about 1.9. 1.9 sigma. So we can now look that up on the graph. 1.9 sigma. So it looks like each of these tick marks is 0.1. So about 1.9, a little more than 1.9 actually, puts us about here on the graph. And then we look up the energy of that point. That looks like we got 2, 4, 6, 8. I think those tick marks are 0.2 each. So we're at about negative 0.7-ish, negative 0.07. So I would interpret that as meaning that the energy of that bond is negative 0.07 epsilon. So the energy of this bond is about negative 0.07 epsilon. And this is not terrifically exact because we're just estimating based on the graph, but that should probably be close enough. So like I said, the energy is going to be, the energy of that bond is some fraction of epsilon. We now know what that fraction is, negative 0.07. So we fill in the 0.07 here. And each particle has 6 second nearest neighbors going out in the hexagonal grid. There are 2 moles of those particles. And this approach still double counts. If we say this particle has 6 second nearest neighbors, and this particle also has 6 second nearest neighbors, we've counted one of those twice. So this would be the bond energy contribution caused by just the second nearest neighbor bonds. And multiply that out, we've got negative 0.07 times 6 times 2 divided by 2 becomes just 0.42. So 0.42 times Na times epsilon. That's 0.42 times 6.02 times 10 to the 23rd times, and then same epsilon, 1.15 times 10 to the negative 22 joules. And then we can multiply those together, 0.42 times 6.02 times 1.15. And again, the 10 to the powers just work out to 10 to the 1. So 2.9 times 10 is about 29 joules, or negative. Don't want to forget those negative signs. So that means that this whole system, all 2 moles of argon, involve negative 415 joules of energy from just the nearest neighbor bonds, plus another negative 29 joules of energy from just the second nearest neighbor bonds. And note that that's pretty small. The negative 29 joules extra from the second nearest neighbor bonds is rather small compared to the contribution from the nearest neighbor bonds. So if we had left out the second nearest neighbor bonds, as suggested in this problem, we'd still get a pretty close estimate. But the nearest neighbor bonds plus the next nearest neighbor bonds together is going to be a very close estimate. Adding in the third nearest neighbor bonds would make it even more accurate, but it's going to be a very small amount of extra. So nearest and second nearest neighbors is probably a good enough approximation for many practical purposes. But generally you want to look, in a test question, you want to look at what's it actually asking for. If it's asking for just nearest neighbor bonds, you would just include this negative 415. If it's asking for nearest and second nearest neighbors, you'd add both of these together to get the total bond energy. If you have 5 particles and can't create a triangle and you want to find the next nearest neighbors, what sort of arrangement would you be dealing with, or what sort of geometry?
3 and then 2 at the bottom. 3 on the top and 2 at the bottom.
You mean like 3 here and then 2 more below it?
Yes, please.
In that case, if you got something like, let's say like here, 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 and then 2 more down here.
Yes.
Tidy that up a bit. In a case like that, the nearest neighbors would just be the adjacent ones. So like this one, this one, this one, and these diagonals are also all adjacent. So those would all be R naught. It looks like we've got 1, 2, 3, 4, 5, 6, 7 of those. So in this arrangement of just 5 particles, we'd have 7 nearest neighbors, or 7 nearest neighbor bonds. The second nearest neighbor bonds would also be the ones through the middle like that. And it looks like we'd only have, what, 2 of those? So we got this one and this one. And note that that's exactly the same as the second nearest neighbor we just drew. That's still going to be a square root of 3 times R naught. And you can't really draw out the same right triangle in this case because we don't have another atom to draw it to. You could certainly imagine an extra atom. If you just imagine filling in an extra particle here, even though it's not physically there, you could still draw it in terms of finding the distances. So you could say you have, this is the distance to R naught, this is the distance R naught, and this is the missing distance we're trying to find. So you could still draw in the same triangle. But even without that, drawing in that extra one, you could still do this using this distance being R naught. This distance, not all the way, but just to the halfway point being half of R naught, and then solve for this distance. That's a right triangle, R naught, half of R naught. Use the Pythagorean theorem to find this missing side. Of course, that's only half the distance, so you'd have to double it also. But you'd still end up with square root of 3 times R naught.
Thank you so much.
And also in that case, since it's a fairly small cluster, we could probably find the exact bond energy, including all the bonds. Because here, using the nearest neighbor bonds and the second nearest neighbor bonds, we've listed everything except for one more bond. We can also do this bond from the top left to the top right. That's the only pair we haven't considered yet. And that, what would that distance be?
2 R naught.
Yeah, so that's just 2 R naught, or 2 sigma, so 2 times 1.12, that's 2.24, so you'd look that up on the graph, and that's going to be an even smaller amount of energy. It looks like maybe negative 0.2 or something like that, or negative 0.02 epsilon. So that's an even smaller amount of energy. Any other questions on that one?
Just to clarify, to find for this one, for the 5 atoms, if we were to determine what the next to nearest neighbors is, would it just be 1/2 R naught squared plus R naught squared is equal to, oh wait, no, it would be 1/2, wait, now I'm confused. What would the Pythagorean theorem look like?
Well, let's take a closer look at that. I think I can, yeah, there we go. Expand that out. So if we take a look at just this triangle, so this side length would be R naught. This side length would be half of R naught. And this side length would be half of the missing distance we're trying to find. So if we label those as such, we've got R naught as the hypotenuse. We've got half of R naught as the known leg. And let's call this half of the unknown distance we're trying to find. So if we write this out as the Pythagorean theorem, we're going to have leg squared plus leg squared equals hypotenuse squared. So r naught over 2 squared plus d over 2 squared equals hypotenuse squared. And you square r naught over 2, you get r naught squared over 4 plus d squared over 4 equals r naught squared. And this will probably be easier to work with if we multiply both sides by 4 before our next step, just to clear those denominators. So we multiply by 4, we get r naught squared plus d squared equals 4 times r naught squared. And then how would we proceed to solve for d there? What would be a good next step?
Sorry, you would subtract r naught squared from the left.
Yeah.
Subtract from both sides, and then you would take the square root.
Right. And note that we still end up with square root of 3 times r naught. So same result, because this is really the same geometry as the hexagonal grid. We're just looking at one small portion of that hexagonal grid. But the distances work out exactly the same.
That makes sense. Thank you so much.
You're welcome. Any other questions on that one? Okay, let's take a look at some of the rest of this problem, because I think some of the later parts of it were kind of confusingly worded. Equal partition, what's the total potential energy on average for the entire solid at T equals 5 kelvins? So assuming we bump up the temperature to 5 Kelvin, and we want to know what's the total potential energy. So here we're going to get into the idea of bonds, or sorry, modes. If we're talking about just this monoatomic solid, how would we figure out the potential energy in all of the potential energy modes? Like how many potential energy modes would each particle have?
For a monatomic solid? Yeah, for a monatomic particle?
Yeah, we're assuming this is a monoatomic solid. So how many modes would we be dealing with?
Monatomic solid, 3.
Yeah, we've got 3 potential energy modes. And of course, 3 kinetic energy modes also, but we're looking at just potential energy. So each particle has 3 potential energy modes. And we want the total potential energy for the entire solid. And the potential energy for the whole solid equals, let's see, we've got 2 moles of atoms.
kBt? Would that
Sorry,
be?
what was that?
Would we use like the 1/2 kBt per mode one for this one?
Yeah, because that's the energy in one mode.
Okay, and then we
if we've got, so 1/2 kB times temperature.
Okay.
So that's the energy in one mode, times 3 modes per particle.
Mm-hmm. And then times Na times 2.
Right, because that's the number of particles. So that'll tell us the energy in all those potential energy modes. Although I think we're going to need to be careful about that, because that's the potential energy portion of the thermal energy. But potential energy includes that portion of thermal energy, and also bond energy counts as potential energy. Because if we go back to the idea of how energy is distributed, the kinetic energy is half the thermal energy. Because the thermal energy consists of kinetic energy modes and potential energy modes. The potential energy of all the molecules is the other half of the potential energy plus the bond energy. Because all the bond energy counts as potential, half the thermal energy also counts as potential energy, the half that's in the potential energy modes. So we're going to have to take this. This is basically the half of the thermal energy that's in the potential energy modes. The other half is in the kinetic energy modes. So we can take that, and then I think we'd have to add the bond energy that we calculated earlier, the negative 415 joules plus the negative 29 joules if we want to include the second nearest neighbors. So we've got our contribution from the potential energy modes from thermal energy, which is really just half the thermal energy, plus the bond energy. That's going to give us the total potential energy. And if we actually calculate that, we've got Boltzmann's constant. What is Boltzmann's constant? Is that like 1.3 times 10 to the negative 22 or something?
(1.38 times 10 to the negative 22).
Okay, thanks. 1.38 times 10 to the negative 23 divided by 2 times the temperature, which is 5 kelvins, times 3 modes. And I think Boltzmann's constant is in joules per Kelvin. Times 5 kelvins times 3 modes per particle times 2 times Avogadro's number plus the bond energy we found earlier, which was negative 415. So multiplying all that out, and the 10 to the negative 23 and 10 to the 23 cancel out. So we just have 1.38 divided by 2 times 5 times 3 times 2 times 6.02, 124.6. So about 125 joules. So that's half the thermal energy. The total thermal energy then would be 250 joules, but half of that counts as potential energy. And then we've also got 415 joules, negative 415 joules of potential energy. So this is just the half the thermal energy plus the bond energy. So that's half the thermal energy is the 125 joules plus negative 415 joules is the bond energy. Add those up, and that should give us the potential energy, negative 290. So we would say that the whole solid has a total potential energy of negative 290 joules. Any questions on that so far?
Yeah, really quick. I have the equation for thermal energy down in my notes as 1/2 kBT times the total number of modes. Would you divide that by 2 in this equation to get thermal energy over 2 plus bond energy?
Yes, although we kind of already did that by using just 3 modes instead of 6 modes, because each particle has 6 modes. So if you use 6 modes, that's 3 translational and 3 potential. If you use 6 modes, you'd get the total thermal energy of the whole solid, and then you divide that by 2, because half of the thermal energy is potential energy. Or we could just say, let's focus on only the potential energy modes. There's 3 potential energy modes per particle. So if we use 3 modes, then the energy we find is just the potential energy. So we don't have to divide that by 2.
I see, thank you.
And someone was asking for thermal energy per molecule versus per atom. It's really more like thermal energy per particle. In this case, the particles we're talking about are individual argon atoms. So there aren't really molecules involved. If it were non-monoatomic, if these were like, let's say, I don't know, liquid, or let's say solid water, you could probably still just treat each molecule as a particle. And we do look at this as on a per molecule basis instead of a per atom basis. So it's really just energy per particle, or number of modes per particle. But in this case, it's monoatomic, so that doesn't really matter. Any other questions on that so far? Why are we adding the bond energy? Because bond energy also counts as potential energy. The way I think of it, bond energy being negative represents that lowest possible energy it could possibly have. The half the thermal energy is how much extra energy above and beyond that we have. In fact, you can even kind of see that on the Lennard-Jones potential energy graph. The negative 415 joules is basically the bottom of the graph added up for all the bonds. The plus 125 joules represents that the bonds aren't all at that lowest value. Rather, the molecules are vibrating, or the atoms are vibrating a little bit. So we've got a little bit higher instead of at the very bottom. And why are we using 3 modes instead of 6? What we just calculated here, the 125 joules we found, is not actually the whole thermal energy. It's just the contribution to the thermal energy from only the potential energy modes. And each atom does have 6 modes, but that's three kinetic modes, the translational motion, and 3 potential energy modes. If we're looking for just potential energy, we can look at just the 3 potential energy modes and ignore the translational modes. So that's what I was doing here. Alternatively, you could use all 6 modes, find the total thermal energy, but then take half the thermal energy, because only half of the thermal energy counts as potential. Yeah, same idea. If we wanted to find the total kinetic energy, we'd use just the 3 translational modes. But this is really why the thermal energy is split up half and half, kinetic and potential. Because of these 6 modes you've got, 3 of them are translational and 3 of them are potential. So that's half of them being kinetic energy and half of them being potential energy. And thanks to the equipartition theorem and the idea of microstates, we should expect the energy to be equally distributed to all the modes. So the 3 kinetic energy modes have the same amount of energy as the 3 potential energy modes, which means the thermal energy should be expected to be split up half and half, kinetic and potential. So that's really where these thermal energy over 2s in the formulas come from. That half the thermal energy counts as kinetic energy, the other half of the thermal energy counts as potential energy, and the bond energy also counts as potential energy because it has to do with how the molecules interact with each other. And the bond energy could be thought of as kind of a baseline. Bond energy is that negative epsilon for all the atoms combined. The plus thermal energy over 2, that's the extra energy they have above and beyond that because they're not actually at equilibrium. They're vibrating because they're not really at absolute 0 Kelvin, actually. Any other questions on that so far? What did they get for B for the answer there? Did they not include the bond energy? Were they looking at just the 125 joules?
Yeah, they didn't include the bond energy.
Okay.
So it's less than what we, I think greater than what we had, yeah.
They really should be including the negative 415 there because the bond energy does count as potential energy. If it was asking like just what's the total thermal potential energy, then yes, I would use just the 125 joules. But if it's asking for the total potential energy of the whole solid, that should be a negative value because it's bonded. If the total potential energy were non-negative, I would expect this to be a gas, not a solid. So realistically, I think we should include negative 290 joules here, or include the negative 415. And number of modes is, oh, that's right. This is 2-dimensional, isn't it? I was thinking 3-dimensional. If this is 2-dimensional, then we should really only have 2 modes per particle. Because the whole reason why modes come in sets of 3 is because we live in a 3-dimensional universe. But if we're treating this as only 2-dimensional, then we really should be saying there's 2 modes per particle. So that 3 is at 2. So we're really only going to get 2/3 of this. Fortunately, I don't have to recalculate the whole thing. I can just take 2/3 of 125 and get about 83. So that should really be about 83 joules worth of thermal potential energy, which we should then combine with the bond energy we already calculated. So 83 plus negative 415 is about negative 332. Any questions on that so far? And then in part C, we want to find the average potential energy per bond. Because what we found here was the, how do we know it's a solid? I think it said so. And also because they're so closely bonded together. Like every particle is bonded to all these neighbors nearby. in a liquid, there would be fewer bonds available. Like there might be, the energy level would allow some particles to be bonded to some particles, but still able to flow around. And then in a gas, they wouldn't be bonded at all. So it's really just the fact that these are all bonded together that tells us it's a solid. But now we want to find the potential energy per bond. We have the total potential energy of the whole system, negative 332 joules. How do we change that into potential energy per bond? What operation does per usually signify in cases like this?
You divide.
Yeah, we want to divide total potential energy divided by total number of bonds. So total potential energy divided by total number of bonds. That'll tell us the average potential energy per bond. And we have the total potential energy, that's negative 332 joules. And the total number of bonds, we actually already calculated that when we were working out the bond energy. And here we're assuming we're specifically just looking at the nearest neighbors. So, so ignoring the second nearest neighbors for now, we've got, which part of this was representing the total number of bonds?
It was 6 divided by 2, I believe.
Yeah, because we had, if we look at just this section, this entire formula is really about the energy per bond times the number of bonds. So everything except the negative epsilon, this 6 times number of bonds per particle times number of particles divided by 2 to eliminate double counting, that is the number of bonds. So if we just fill that in for total number of bonds, we can just take the total potential energy divided by that total number of bonds, and that'll tell us the energy per bond, potential energy per bond. So total potential energy, negative 332 joules, divided by total number of bonds. The 2's cancel out, so we should just get 6 Avogadro's number. So negative 332 joules divided by 6 times 6.02 times 10 to the 23rd. So 332 divided by about 36. I'm getting about negative 11,991.92 times 10 to the negative 23rd. We can shift that decimal point over a bit. 1, 2, 3, 4. 4 makes it 19. So that's the potential energy per bond in joules, but we'd like to write that in what units instead.
Epsilon?
Yeah, we want to put that in terms of epsilon. And I think we've got a conversion there, 1.15 times 10 to the negative 22 joules. This doesn't seem right. That's going to be way too many, isn't it? Did I get that wrong? 23rd. Yeah, that seems right. Except that means we're going to end up with like several hundred epsilon. Why is that not going to work? Did I forget something there? My concern here is that if we convert this into epsilon by just multiplying, let's round this off to about negative 1.2 for now. If we convert this into epsilons by multiplying it by, what was epsilon again? We've got 1.15 times 10 to the negative 22 joules. So we're going to have to multiply this by 1 epsilon divided by, I should just write that down, 1.15 times 10 to the negative 22 joules. That way, if we divide, then the joules are going to cancel out. We end up with epsilons. My concern is when we actually divide this, we're going to get something like 100 epsilon. The 1.2 and 1.15 mostly cancel out, but 10 to the negative 19 divided by 10 to the negative 22 is 10 to the third. So we get about negative 1,000 epsilon. That doesn't really make any sense as the energy per bond, does it?
I got a different value for the negative 1.1.
Okay, and what did you get?
I got negative 9.19 times 10 to the negative 23.
Okay, that sounds more reasonable. What did you do to get that?
Oh, I did. I just think maybe you plugged it differently, but I got 9. It was the same thing. I just think you plugged it wrong in your calculator.
Oh, so I did.
Yeah.
Maybe I should be dividing instead of multiplying. Thank you.
Okay, yeah.
I thought that sounded absurdly large. Okay, yeah, about 9.2. Yeah, thank you. That
negative 9.19.
Okay.
And then to the negative 23.
Yeah, that sounds much more reasonable. Thank you. Yeah, because that way, negative 9.19 times 10 to the negative 23, when we actually divide these, because we're still just dividing by 1.15 times 10 to the negative 22 joules to get joules to cancel out and introduce epsilon. So 9.19 divided by 1.15 is about 8. And then 10 to the negative 23 plus 22 becomes 10 to the negative 1. In other words, about negative 0.8 epsilon. So that's much more realistic. We should expect something between 0 and negative epsilon. And this is negative point epsilon is the potential energy per bond. Any questions on that so far? All right, so let's see if we can turn that into information on a graph now that we know the potential energy, negative 0.8 epsilon. And that's the average potential energy. But it says here that in a simple spring mass system, the maximum potential energy is twice that much. Well, really, we should treat that as twice as high above above the lowest point. Because if we go back to the original graph, and keep in mind here, we're talking about finding R min and R max. So if we go back to the graph, move these to the side. Going back to our potential energy graph, we know that the average potential energy is negative 0.8 epsilon. So that is right here. That is our average potential energy of that one bond. And the reason why we want for one bond in the first place is because that's what this graph is talking about. The Lennard-Jones potential graph is all about one single pair, one single bond. So if we're treating negative 0.8 epsilon as the average bond energy, but it tells us that the maximum potential energy is twice that average. Because if you got, if the particles are oscillating, then they're going to spend some of their time near equilibrium, which is very low potential energy, and some of them close or far, which is very high potential energy. The average potential energy is halfway between those lowest and highest values. What's the lowest potential energy possible here? If these particles are oscillating, what's the lowest potential energy they could possibly have?
Negative epsilon.
Yeah, -1 epsilon is the lowest value on this graph. So there's our minimum potential energy. If we know the minimum is -1 epsilon and the average is -0.8 epsilon, what would you expect to be the maximum potential energy? -0.8 is the average between -1 and what?
Minus 0.6 epsilon.
Yeah, -0.6 epsilon would work as potential energy max. And there are a few ways you can interpret this. One way is to literally just look at the -0.8 as the average of -1 and something. -0.8 is halfway between -1 and -0.6. You could also use the hint that they give you down in this problem where it says, in a simple spring mass system, the maximum potential energy is twice the average potential energy. But for a simple spring system, we're treating 0 as the baseline. 0 is the lowest potential energy. Here, the bottom of the graph isn't 0. The bottom of the graph is negative epsilon. Our average is 0.2 above the bottom. So we should expect the maximum to be twice that far above the bottom. So go up 0.2 and then up another 0.2. There's your maximum potential energy. And if we want to compare kinetic and potential energy, we expect the maximum potential energy when the kinetic energy is what?
At its lowest.
At its lowest, which for kinetic energy is going to be 0 because you can't have negative kinetic energy. So if the potential energy is -0.6, then kinetic energy should be 0. So E total is -0.6 plus 0. In other words, that -0.6 is the total energy. So we can actually draw out a total energy graph. The total energy is just at -0.6. That's the total energy for a single pair bond. And if we know the total energy and the potential energy graph, how do we find R min and R max?
Where kinetic energy will be 0.
Yeah, kinetic energy is 0, and kinetic energy is going to be 0 under what circumstances? What should we be looking for on these graphs?
Where it crosses the x-axis?
Well, that's where the kinetic energy graph is going to cross the x-axis, but we don't have that graph yet. What should we be looking for on the potential energy and E total graphs?
Where,
sorry, go ahead.
Mm-hmm.
Maybe where total energy intersects with the potential energy graph?
Yeah, that should work, because if total energy equals E total, there's nothing left for kinetic energy. So at this location and this location, at those two locations, potential energy equals E total, which means kinetic energy is going to be 0. So we look at those R values on the R axis. Those should be R min and R max. So our kinetic energy graph is just going to hit 0. I mean, if we actually wanted to draw out a kinetic energy graph, it's going to hit 0 at those 2 points. And then in between, it's just going to be a mirror of the potential energy graph. But those will be R min and R max. Looks like approximately 1.0 something and 1.3 something. And this is still just an approximation because we don't have a tremendously precise way of getting values from this graph, but around 1.0 something and 1.3 something, maybe 1.05 and 1.35. Any other questions on that one?
Could you also determine R min and R max from, I know there's a Leonard-Jones equation. I'm not exactly sure what it is by heart, but is that a more accurate way, I guess, of determining those values?
Yes, that would be more accurate. The only problem is that the equation, if I remember correctly, involves something involving r to the 6th and r to the 12th. So in that case, you'd have to be solving for r. If you had an R value and you wanted to find the energy, then that would be fine. You just plug in the R value. But in this case, we have the energy. We want the energy to be negative 0.6 epsilon. And we want to find the R value that makes that true. And the problem is that's going to involve solving this 12th degree polynomial. And I don't know how to do that. You could just try guess and check method. You could approximate it from the graph and plug in values for R that are what you've got here. Like let's say plug in 1.05 for R, see what potential energy is. And if it's very close to negative 0.6, then that's fine. If it's a little far from negative 0.6, try adjusting the R value a little bit left to right and see if you can get the result closer to negative 0.6 epsilon. But in this case, I think I would just estimate it from the graph.
Sounds good. And then just one more question. How did you determine where the total energy lies?
The total energy should be at the maximum potential energy, because maximum potential energy occurs when kinetic energy is 0. And we know the maximum potential energy is as far above PE average as PE average is above PE min, because average potential energy is halfway between the minimum and maximum.
Okay, makes sense. Thank you.
Any other questions on that? Yeah, the maximum kinetic energy would be 0.4 epsilon because that's the difference between the total energy and the minimum potential energy. In other words, this difference between kinetic energy or lowest potential energy and the total energy, that's the largest the potential or largest the kinetic energy can be. Because kinetic energy is going to be the difference between E total and potential energy, and this is the largest that difference can get. Any other questions on this one? All right, then let's take a look at some other examples. We've got plotting energies, Leonard-Jones. I think that covered a lot of this stuff, really. We got modes, bond lengths, particle model of matter, bond energy, nearest neighbors, next nearest neighbors. Let me pull up some of the other requests. Somebody was asking for summer session 1, 2018, and problem number 2. Let me see if I can find that.
Oh, you actually already answered my question for that one. It was the one with the 5 atoms.
Oh, right, that one. Okay. Then let's see what else we've got. Let me pull up this one with the pressure volume graph that someone sent me earlier. So here we've got a pressure volume graph, a 4-step cyclic process. And we know that let's just start listing out everything we know about these processes. I find that's usually a good way to start this, just to, I'm not sure which problem is this. Somebody sent me this just as a screenshot. Was this from Henna, I think? Henna, do you know which test this came from originally?
I think it's 2020 summer session 1.
Okay. So if we just start listing out everything we know about each of these 4 processes, I find that's usually a good way to start situations like this. That if we take a look at, for instance, process A from 1 to 2, we know process A is constant pressure. So that's isobaric. And then process B from 2 to 3, we're specifically told is adiabatic. And what does that mean?
It means there's no heat.
Yeah, no heat at all. So if the thermal energy is changing, but it's changing due to work, not due to heat. And then state 3 to state 4, process C, we know it is constant pressure again. And then process D, taking us from state 4 back to the original state 1, is isochoric, constant volume. So if it's constant volume, what does that tell you about work?
No work is being done.
Yeah, no work at all. So that's useful to know. We know that there's no work, so any change in energy must be from heat. And typically in a case like this, what we usually what we usually care about is for each one of these processes and or for the whole system, the whole cycle, I mean, we usually want to know what's the work, what's the heat, what's the change in energy for each one of these steps and for the whole cycle. So let's see if we can start listing those out. If we just want to find, I mean, this is probably what we want to figure out eventually anyway. Let's look ahead and see what we want to know. We're going to want to know volume at state 2 because it doesn't tell us what that volume is. It tells us all the other pressures and all the other volumes, but it doesn't tell us the volume at state 2. And also area bound by the curve in process B versus the volume axis. So that's presumably just amount of work for B. And work in joules per second if the cycle repeats every 5 seconds. So that's going to mean we're going to need the work for the whole system or whole cycle. So if we just start saying, if we just say, we're going to want to know heat A and work A and delta U A. And presumably we're going to need these for all of them. We're going to want heat B, work B, and delta U B. And likewise, we'll want heat C, work C, delta U C. And heat D, work D, delta U D. And I think this is just going to be a very useful way to organize all that information because we're going to probably need all of these pieces of information. So let's try this. Are there any of these that we know right away, just from the type of process involved?
Yeah, so for process B, QB will be equal to 0.
Yeah. We know heat B is 0 because it's specifically just stated as adiabatic, which tells us that work B and delta UB are the same value. So if we know either one of those, we immediately know the other. Anything else?
And then for D, work would be equal to 0.
Yeah, definitely 0 work there. And because that's isochoric. And are there any other ones we can find by any other means? Do we know anything else here? Can we figure out any of the other works or heats or changes in energy?
Yeah, you could calculate. You could calculate work at C just by finding the area of the rectangle under the curve.
Yeah, we can find that rectangular area. This area is the amount of work. The work for C specifically. So if we just take that, the pressure, 50 pascals, and the change in volume, which is what, 0.0161 cubic meters, that should tell us the work done here. So we've got 50 Pascal, or 50,000, because there's a times 10 to the third, times the change in volume, which is 0.0161 cubic meters. So 50,000 times 0.0161 is about 805 joules of work. Also, we need to make a decision about whether to treat that as positive or negative. What's happening to the volume during process C?
It's decreasing.
Yeah. Volume is decreasing. If you're compressing this gas, are you doing work to the gas, or is the gas doing work to its surroundings? Yeah, we're doing work to the gas by squeezing it into a smaller space. Work is entering the gas, so we'll treat that as a positive value. So that's the work for C. By calculation on the graph, by just calculating that area, we find the work is positive 805 joules. It also tells us that in process A, we've got 2,500 joules of energy entering as heat. So heat A is just given, plus 2,500 joules. So that fills out a few more values. Are there any other values we could calculate here, or any other given information? Do we have any ways of calculating the delta U involved here? Oh yeah, we could calculate work for A, right? Because that's also, wait, do we have that value? We don't know V2, right? We could at least work it out in terms of V2. Let's see if we can write it out using V2 as our unknown, as it just some. So in this region, we know we have work for A is pressure, 200,000 pascals, times the change in volume, which we don't know. Delta V is going to be V2, which we don't know, minus 0.01 cubic meters. Also, should we treat this as a positive or negative value? Yeah, this should be negative. In general, work is going to be negative P times delta V. And we should expect a negative value here because the volume's increasing. So that'll be negative 200,000 pascals times V2 minus 200,000 times 0.01, which will just be 2,000. So that's the work done during process A. Oh, I guess that's negative times negative though, so that's plus. So the work done during process A is negative 200,000 pascals times V2 plus 2,000 joules. So we could fill that in. We just don't know what V2 is yet.
Where did the 2,000 joules come from? Sorry.
That's the 200,000 times 0.01. So I'm just distributing the 200,000 to both of these terms. 200,000 times V2 minus 200,000 times 0.01.
Okay, thank you.
Mm-hmm. So we don't know how much work that is, but we at least know it's written in terms of V2. The 0.0161 meters cubed in the work for A was from subtracting the volumes. So for A, we had a final, for process C, we had a final volume and an initial volume. So final minus initial would be 0.0161. Any other questions on that so far? And we can't really calculate work B yet because we don't really have a good way of finding the area under this curve. For D, we know the work is 0, but we don't really have a value for heat yet. It looks like to go any further, we're going to need some values for delta U. So any thoughts on how we could do that? How can we find the delta U values?
For D, could you use like 1/2 times the moles per particle times the volume times the change in pressure for Q?
Yeah, I think that'll work well. We've got, and from the usual delta E thermal formula, we've been using 1/2 times number of modes, or just number of modes over 2, times N times R times delta T. But NR delta T could just be replaced completely with delta PV. And do we know how many modes we're dealing with here?
3, because it's a monatomic gas.
Sounds good. Number of modes equals 3 because monatomic gas. So filling that in, we get delta E thermal equals 3 over 2, or just 1.5, times delta P times V. So if we can just find the difference in pressure times volume for a given process, and then multiply by 1.5, we'll have the delta U, delta thermal energy. So let's try that for each of these processes, because for each process, we can find delta PV, although we still don't know volume 2, but we can maybe find that. So finding delta PV for each process, then multiplying by 1.5, that'll give us values for all of those delta U's. So let's start with A, for instance. For process A, we can say delta U equals 1.5 times P final V final minus P initial V initial. So let's say P2 V2 minus P1 V1. We know that the pressure is not changing though, so we can actually factor pressure out of this. We don't know what V2 is, so we're leaving that as an unknown, but we know V1 is 0.01. .01 meters cubed, and we know the pressure is 200,000 pascals. And again, we can distribute that. We've got 1.5. First of all, 1.5 times 200,000 would be 300,000. Times V2 minus 300,000 times 0.01 would just be 3,000. And then pascals times cubic meters is joules. So again, we don't know V2, but we now at least have an expression for delta UA. So we'll fill that in. 300,000 pascals times V2 minus 3,000 joules. Any questions on that so far? And then we can do that same sort of calculation for all the other steps, all the other processes, B, C, and D. But before we do that, let's focus on process A. We know the heat. We have work in terms of V2, which is an unknown. And we also have delta U in terms of that same unknown V2. What do we know about how those are related though? Heat, work, and delta U.
By the second law of thermodynamics, it's, yeah, delta U is equal to Q plus W.
Yeah, that should work really well. We can use this to solve for that unknown V, I think. That we know that delta U equals heat plus work. So if we fill all that in, delta U is our 300,000. I'm going to leave off the units here since it's all in pascals, cubic meters, and joules anyway. 300,000 times V2 minus 3,000 equals work plus heat. 2,500 plus 2,000 minus the 200,000 V2. And how could we use this to solve for V2 then?
We would just have to factor V2 out and.
Yeah, although before that, we can't really factor V2 out until it's all the V2s are on the same side of the equation. So I think what we're going to want to do here. Yeah, let's try moving things around. Let's say add 200,000 V2 to both sides. So that'll cancel out the negative 200,000 V2s. And while we're at it, let's also add 3,000 to both sides to cancel out that negative 3,000. And let's see what's left. 300,000 V2 plus 200,000 V2 is 500,000 V2. And then we've got 2,500 plus 2,000 plus 3,000 for a total of 7,500. And then what? How do we isolate V2 here? What's our last step for solving for V2?
We just divide by 500,000.
Yeah, divide by 500,000. And we get about exactly 0.015 cubic meters. And fortunately, that seems to be between 0.01 and 0.0261, so that seems entirely reasonable. That is V2. So we now know the value of V2. So V2 is 0.015 cubic meters. And now that we know that, we can fill that in all of the, or the two locations where it showed up earlier, work A and heat A, or delta UA. Any questions on that so far? So let's go ahead and fill those in. Now that we know V2, we've got work A is 2,000 minus 200,000 times 0.015, which is negative 1,000. And delta UA is 300,000 times 0.015 minus 3,000, which is positive 1,500. And note that heat plus work equals delta U, exactly as we should expect. Any questions on process A so far? And now that we know V2, I think we can figure out delta U for process B as well, because now we know everything about point 2 and everything about point 3. So we can use our usual delta E thermal formula, 1.5 times delta PV, to figure out the change in energy there. So let's try that. Now that we actually have V2, we can say for process B, delta UB is going to be 1.5 times P final V final minus P initial V initial. We're ending at 0.3, so that'll be P3 times V3. And we're starting at 0.2, so P2 times V2. And we can start filling in some values there. And note that we can't factor out either one of those. The pressure's changing and the volume's changing. So we actually need final pressure times final volume minus initial pressure times initial volume, delta the whole thing. But if we multiply at 0.3, we multiply 0.0261 times 50,000. 0.0261 times 50,000, that's 1305. And then P2, V2, so V2 that we already found, the 0.015, times pressure 200,000, and that's 3,000 joules. So that difference, 1305 minus 3,000 times 1.5 is negative 2,542 and a half. So that should be the delta energy for that process. Any questions on that so far?
And then that would also be equal to the work, correct? But the work would be negative. Exactly,
because we know that heat is 0. So filling in the delta U we just found, negative 2,542.5 joules. And we know that there's no heat involved because it's specifically labeled as adiabatic. So work is the same as delta U. And yeah, the fact that it's expanding matches up with the expectation that it should be a negative value. So we now know everything we need to know about process B. No heat, negative 2,542.5 joules of work, that is work leaving the system as we allow it to expand, and also negative 2,542.5 joules of change in energy. It's getting colder as it expands. Any questions on process B? All right, then let's try applying the same steps to process C and process D, because in both of those, we know the amount of work. If we can find delta U, then that's the same as the amount of heat. So for process C, we've got 1.5 times delta PV, so that's P final times V final minus P initial times V initial. Although in process C, what is not changing?
The pressure.
Yeah, it's the same pressure. P3 is the same as P4. So we can just factor out P4. And filling in the values there, we know P4 is 50,000. V4 minus V3 is just 0.0261 minus 0.01, so that'll be 0.0161 meters cubed. Multiply those together, 1.5 times 50,000 times 0.0161 is 1207 and a half. And that's positive, corresponding to, wait, does that make sense? Oh, I should be subtracting final minus initial though. V4 minus V3 is negative 0.0161. So we actually are losing energy. I was suspicious about that because if we're going to the left on the graph, think back to ideal gas law. If you're holding pressure the same but decreasing volume, what should you expect to be happening to temperature?
Will it be decreasing?
Yeah, we go back to PV equals nRT. Pressure is constant because this is an isobaric process. If the volume decreases, we should expect the temperature to decrease also. Those should be proportional to each other. So if we're going straight to the left on the graph, that should correspond to a drop in temperature, and therefore delta U should be negative. So keep watch for things like that. Look for situations where you know delta U has to be positive, or you know delta U has to be negative, or work has to be positive or negative or whatever. Make up expectations like that ahead of time, and then watch the numbers as they develop from the calculations to make sure they match up with what you should expect. If they don't match up, either something's gone wrong with your calculations and you should double check that, or something's wrong with your expectations and you should double check that. But watch for discrepancies like that. That means something needs to be corrected. This negative 1207.5 though looks like it's fine, so we'll fill that in for delta U for process C. And with that, what else can we immediately calculate? What's the only unknown left for process C now?
Q would be delta U minus delta.
Yeah, because we still have first law of thermodynamics, Q plus W equals delta U. So Q is going to be delta U minus work. And we know both of those, delta U, negative 1207.5, minus work, 805. We get negative 2012.5. So that would be the heat involved in process C. You've got to have a lot of heat leaving the system and a little bit of work entering as it condenses or as it gets compressed. And then this is our actual change in energy. Looks like all that's left is process D from 4 to 1. And we can use the same approach, calculating delta PV times 1.5. So for D, we got 1.5 times, looks like that'll be for final minus initial, P1 V1 minus P4 V4. In process D though, what's not changing?
Volume.
Yeah, so we can factor out volume. It's just volume times P1 minus P4. And the volume is 0.01. Difference in pressure, final minus initial is 200 minus 50, so 150,000 pascals. And that is positive because we're doing final minus initial. So 1.5 times 0.01 times 150,000 is 2,250. So that would be the delta U for the process D from 1 to 4. And since there's no work, the heat is exactly the same, plus 2,250. So it looks like we've now filled in this entire chart. We know the heat, work, and delta U for every single part of this cyclic process. Any questions on that so far? And at this point, I think we can also find the total heat, total work, and total change in energy. Let's try adding those up. So the Q for one full cycle, the work for one full cycle, the delta U for one full cycle. If we add up all the heat, we've got, so 2,500 plus 0 plus negative 2012.5 plus 2250, I'm getting 2,737.5. So that means over the course of one full cycle, we are adding that much heat to the system. And then we add up all the work. We got negative 1,000 plus negative 2,542.5 plus 805 plus 0. And I'm getting negative 2,737.5. Why are those exact opposites? Why do those have to be exact opposites?
Because delta U is a state function and this is a cycle, so delta U will be equal to 0.
Exactly. For any complete cycle, any state function returns to its starting value. So the initial energy is the same as the final energy. Like let's say we start at point 1, we have a certain amount of energy. Go around the cycle, get back to point 1, we have the same amount of energy. So these changes should be expected to add up to 0. As one final check, we can add up all these delta U's around the whole cycle. So 1500 plus negative 2542.5 plus negative 1207.5 plus 2250. And yeah, those add up to exactly 0. And in practice, sometimes you'll end up with like a small difference from 0 because of a rounding error. But if everything's exact, then it should add up to exactly 0. So that fills in all the values we're going to need. We've got every heat, every work, every delta U for both each process individually and for the entire cycle. Any questions on that so far? One other thing about the graph, a very useful way to interpret work, for any single part of the process, work is just area under that curve all the way down to the axis. But if we're talking about a cyclic process, what's a good way to interpret work for the whole cycle? If we're looking at area under the curve, right? So we've got area under this curve. So that's the work done during process A. And then area under this curve, all the way down to the axis. That's the work done during process B. And by the way, would those works be treated as positive or negative?
Negative.
Yeah, this is a negative amount of work so far because we're talking about the gas expanding. So during processes A and B, we've got this much work done as a positive, as a negative. But then what about during process C?
Work is positive.
Right. Process C, we've got this much positive work. Specifically this rectangle here. So if we've got this much negative work plus this much positive work, what happens to the overlap? If you add this negative rectangle plus this positive rectangle, what happens to them? Yeah, they're going to cancel out. So all that's left is the area inside the curve. If you've got a cyclic process, the total amount of work is the area enclosed inside that curve, because everything under the curve everything under the bottom part of the curve cancels out. So all that's left is the area inside the curve. So this is a very useful shortcut for cyclic processes. If you want to know the total work done in one full cycle, just look at the area enclosed inside the curve, and that's the amount of work for one full cycle. As for whether it's positive or negative, usually you just want to take a look at the topmost curve, like the uppermost curve here, A and B. A and B are talking, the topmost curve is the one that's going to dominate because that involves the most work. A and B involve the gas expanding, so that is a negative amount of work. So the total amount of work done during one cycle is going to be negative area enclosed inside the curve. On the other hand, if the cycle had been counterclockwise instead, if the uppermost curve had involved contraction instead of expansion, then we say that's a positive amount of work. This also applies to temperature entropy graphs, by the way. For a temperature entropy graph, what's the area under the curve going to represent? For pressure volume graph, area under the curve is work. For a temperature entropy graph though, what's the area under the curve? Yeah, that's going to be heat. So if you're graphing entropy versus temperature and you just have some process, the area under that curve all the way down to the axis is heat. But if you've got a cyclic process graphed on a temperature entropy graph, the area enclosed inside that cycle, inside that loop, is the amount of heat during the entire cycle. So the same concept still applies, just heat instead of work. Any other questions on what we've done with this graph so far? And generally for any cyclic process, I would highly recommend writing out a list like this, or even put it together as a chart or a data table, whatever you find most useful for organizing the information. But typically in a cyclic process, it's a good idea to be looking for the heat, work, and delta U for every individual sub-process, every side of this shape, and also the total values. Fill in everything you know, start filling in other stuff you can calculate based on the graph, and then start looking for connections. Like for every piece of the process, heat plus work has to equal delta U. And for the entire total process, you should expect delta U to add up to 0. And do we need to find anything else here? What's the volume at state 2? We've got volume 2, area bound by the curve, or in process B, that's just the amount of work. So we found work for B. And work, oh, here we go. There's one more question here. What's the work rate? That is how much work per second, how many joules per second, if this cycle repeats every 5 seconds? Well, we know the amount of work per cycle, right? We've got negative 2,307.5 joules per cycle. If the cycle repeats every 5 seconds, so 5 cycles per second, let's see if we can write that in terms of joules per second. Because we want to know in part C, work rate, work over time, if the cycle repeats every 5 seconds. So we want to know work over time. Work over time. We know how much work is in one cycle. We know that that cycle repeats every 5 seconds. So if we just divide those, work for one cycle, and let's even put units here. This should really be joules per cycle. And then we're dividing that by time. Delta time is 5 seconds per cycle. Cycles and cycles cancel out. We get whatever this is, negative 2737.5 divided by 5. So that looks like negative 547.5 joules per second. Cycles and cycles cancel out, so we're left with joules per second. And that would technically be power, because that's a rate at which energy is being transferred. Joules per second is watts. Any questions on that? And note that overall, over the course of each cycle, are we adding or removing heat? Yeah, positive value for Q means we are putting heat into the system. And meanwhile, what's happening with work? Yeah, work is leaving the system. So what we have here is a device where every 5 seconds you add some heat, you get some work out of it. Add some more heat, get some more work out. Add heat, get work. This machine is turning heat into work. Anyone know what we call that? If you've got a machine that can do work to other stuff. This is an engine. Specifically, we call it a heat engine. You could also kind of treat it as a fridge in the sense that you could use this to extract heat from something. So this could be used as a refrigerator, but might not perhaps be the most efficient refrigerator. But I would call this a heat engine in the sense that it can be used to turn heat into work. If you add heat to this and you get work out of it, you could, for instance, maybe take this machine, put it over a fire so you're constantly putting heat into it, and attach the piston to a crank so it's constantly doing work to something else. So this is one example of a heat engine, turning heat into work. And also, since it's extracting heat and dumping it somewhere else, you could also treat this as, is that a fridge? I don't know if that would actually count as a refrigerator because it's not really, I don't know if it would be dumping the heat to a hotter place. I think a refrigerator, you specifically need to be dumping the excess heat to somewhere else that's hotter rather than somewhere else that's colder. So that can be something very specific. But the fact that we're getting work out of it means we can treat it as an engine. Any other questions on that? All right. Any other questions or any other topics you want to work on before we go?
I have a question. Could you discuss a little bit about the relationship between heat capacity and solving it from the slope of a graph, or determining it from the slope of a graph?
Yeah, which graph in particular? Or which kind of graph?
I don't have an exact question. Actually, I can look for it really quickly.
Okay.
Okay, so it's the fall 2017 practice exam.
Okay, let me see if I have that one. Fall 2017. I'm not sure if I actually have that one. Could you put that in the chat?
Yeah, no problem. Just 1 second.
Okay, there it is.
So it's number 4.
Okay. Okay, this one here.
Yeah.
Well, it looks like we're talking about a graph of temperature versus energy, right? So if we want to make that graph, any line on that is going to have a slope. If we just have some line on this graph, what would the slope of that line be?
Assuming the heat capacity.
Yeah, because we've got, if we're looking at rise over run, rise is delta E. And the run is delta temperature. So the slope here is going to be rise over run, delta energy over delta temperature. And assuming constant volume, delta energy is heat. So this is just heat capacity. So that's heat capacity at constant volume. So if you know the heat capacity at constant volume, which I think is given here, does it tell us anything about? It doesn't really tell us heat capacity, but I think we can find it using the fact that it is monoatomic solid to start with, and then becomes a diatomic gas when it becomes gaseous. So we can calculate the heat capacity based on modes, and then use that to establish the slope. Because generally, heat capacity at constant volume is just the, if we go back to the thermal energy formula, our usual 1/2 kBT, or delta T, times number of modes times number of molecules. And in this case, I'm going to use number of molecules instead of anything involving moles or Avogadro's number because it tells us there's only 50 atoms. So N is just going to be 50. We want heat capacity though. So how do you convert delta E thermal into heat capacity to find the slope?
You have to divide by the change in temperature.
Right. So the delta E thermal divided by delta temperature is just going to cancel out delta T. So this is going to give us the slope. If you just calculate KB over 2, so that's 1.38. Was that 1.38 times 10 to the negative 22? And then divided by 2 times number of modes times number of particles, which is 50. So if we multiply that out, we got 1.38 times 10 to the negative 22 times 50 divided by 2, so that's just times 25. So that'll be 3.45 times 10 to the negative 21 times number of modes. And I'm leaving number of modes as a variable here because that's going to change. For instance, if we've got just a monoatomic solid, what's the number of modes?
3.
Yeah. Wait, is it just 3? It can move in 3 dimensions, but what else can it do?
Oh, sorry, 6.
Yeah, because we've got the 3 translational modes and 3 vibrational modes.
Is this a monatomic gas? Oh, we're talking about a solid. Right?
Yeah, because we're really, if we want the 3-phase diagram, we really need all three phases, solid, liquid, and gas. However, we can treat solid and liquid as essentially equivalent here. Both of those would have just 6 modes. Because whether it's a solid or a liquid, it's in a bonded state. So the molecules or the atoms have 3 translational modes because they can move, and 3 vibrational modes because they can interact. So that means the slope in solid or liquid form is going to be that 3.45 times 10 to the negative 21 times 6. So we multiply that times 6, we get 2.07 times 10 to the negative 20 joules per Kelvin. So that's the slope for solid or liquid form. And ultimately, we're going to be graphing just some lines. We now know the slope of those lines if we're in solid or liquid form. But then when it turns into a gas, it becomes a diatomic gas with vibrational modes frozen. So how many modes would we expect that gas to have?
5.
Yeah, it should be 5 modes per particle. So we would have, oh, we got to be careful though, because if it's forming into a diatomic gas, if you've got 50 atoms and they form into diatomic molecules, how many diatomic molecules do you now have?
Half that amount?
Right. So we're going to need to rethink this. We're going to have slope equals 1.38 times 10 to the negative 22 joules per Kelvin divided by 2 times 5 modes per particle. But now instead of having 50 atoms, we have 25 molecules because the pairs of atoms have bonded together as molecules. So let's see what that's going to be. We've got 1.38 times 10 to the negative 22 divided by 2 times 5 times 25. So we're getting a slope of yeah, that should work. Or in order to make this consistent, since this is all marked in 10 to the negative 20 anyway, 10 to the negative 21, that is the energy axis here is marked in 10 to the negative 21 joules. I'm going to convert the 2 times 10 to the negative 20 into 20 times 10 to the negative 21. So increase or move the decimal point over one space and decrease the exponent. That also makes these easier to compare. 8.625 of something versus 20.7 of something. So this is the slope of the temperature versus energy graph in the solid and liquid phases versus the slope in the gas phase. So now we at least know what the slope is. But we're going to need some starting points. If we want to know where to start this, let's say we go all the way to the left, all the way to the 0 Kelvin side. If our temperature is at 0 Kelvin, we've got no thermal energy. So what's the only kind of energy we have?
Bond energy.
Right. And it tells us the total bond energy of the solid is negative 350 times 10 to the negative 21 joules. So we can use that as a starting point. The energy at the very beginning, at 0 Kelvin, the energy is this value, negative 350 times 10 to the negative 21 joules. So let's mark a point there, negative 350 times 10 to the negative 21 joules. And then if we add energy to the solid, we're going to have the temperature increasing. And we know what the slope is. The slope is going to have to be this 20.7 times 10 to the negative 21 joules per Kelvin. So up 20.7 over 1, up 20.7 over 1, and so on, until we get to what temperature?
75 Kelvin?
Yeah, 75 Kelvin is going to be the melting point. So let's put a mark there. We know something strange is going to happen at 75. So just as a reminder, we're going to put this mark at 75. So there's the melting point, and then the boiling point.
125?
Yeah, so we'll put a mark at 125 also. So we've got the solid phase, the liquid phase, and the gaseous phase. And we know what the slopes are going to be, 20.7 and 8.625. We could even figure out exactly how far it goes, because we know that the slope, if we look at just the solid phase, slope equals delta E over delta T. We know the slope, we know delta T, so we can find delta E. Slope times delta T. Note that this is really just change in thermal energy equals heat capacity times delta temperature, like it always was. We're just writing it in terms of a graph here. Slope 20.7 times 10 to the negative 21 joules per Kelvin. And change in temperature from 0 to 75. So we multiply those together. 20.7 times 75. And I'm getting, it seems kind of high. Right. Because I'm getting about 1500 and we're not going to have room for that on the graph. Are we? 1500. Did we mess up on the number of modes there? We should have 5 modes, right? Did I get the right value for Boltzmann's constant? Is that 1.38 times 10 to the negative 22, or should it be something different?
For the slope of the monatomic solid and liquid, I got 2.07 times 10 to the negative 21.
Okay, did I just miss the value for Boltzmann's constant by an order of magnitude?
Yes.
Is that supposed to be 10 to the negative 23 there?
Yep.
Okay. This is why one must always be careful with orders of magnitude. So that's actually going to be 1 order of magnitude smaller. And that means this one will be also. So if we use instead the correct value of 20.7, or sorry, 2.07, we're going to get approximately 155.25. So let's say about 155 joules. That means the process of raising the temperature to from 0 to 75 involves increasing the energy by 155. So we'll be going from negative 350 to, I guess this should actually have times 10 to the negative 21. But it's all going to be in times 10 to the negative 21 joules anyway. So from negative 350, we add 155, and that puts us at negative 205, I think. Negative 350 plus 155, negative 195. So that means our next stopping point, our next waypoint here is at 75 Kelvin and negative 195. So let's mark that on the graph. Negative 195, pretty close to 200, right about there. So that represents the energy when we get to the melting point, 75. And in between, we should just have a straight line, because we've got this consistent, constant value for a slope. But if we keep adding energy, what's going to happen?
It will change phase.
Yeah, it's going to change phase. So we're going to add energy, raise the energy, but that's not going to change temperature because the phase change happens at 1 constant temperature. And the amount of energy it's going to increase should just be our delta H from solid to liquid. It's not specifying joules per Kelvin or joules per mole or joules per kilogram or something. So I assume this is just joules for those 50 atoms. So from where we are now, we would just be adding 50 times 10 to the negative 21 joules. And we should probably mark where we are on the graph. This is E equals negative 195 at this point. We add 50, we're now at E equals negative 145. So that will be around here. We're increasing the energy to change the phase, but we're not changing the temperature. So that's our phase change. And now that's E equals negative 145. At that point, it's now a liquid. If we keep adding energy to that, what's going to happen?
The temperature will rise.
Right, temperature rises. And we can predict that again using the same sort of formula. Slope equals delta energy times delta time. So during the liquid phase, again, delta energy is going to be slope times delta temperature. Slope is still 2.07 times 10 to the negative 21. But what's the temperature change from melting point to boiling point? Yeah, 50 Kelvin, multiply those together. 2.07 times 50. So we get about 103.5 joules per Kelvin, or joules, yeah, 10 to the negative 21 joules. So from the 145, we add 100, let's just round that off to about 104. Negative 145 plus 104 is going to be negative 41. Yeah, so that means we're going to rise up to negative 41 joules by the time we get to 105 temperature. So 125 temperature, 125 temperature, 41 joules, negative 41, so that'll be just above negative 50. E equals negative 41 joules, or negative 41 times 10 to the negative 21 joules. So we'll have a line from here to here. But then once we get to 125 Kelvin and we add more energy, what's going to happen?
Another phase change from liquid to gas.
Yeah, phase change from liquid to gas, and we know from the delta H listed how much energy that's going to give. So we add to negative 41, we add 250. And that gets us to 209 joules. So the next stopping point is going to be E equals 209 times 10 to the negative 21 joules. And so we put a point there, 209, somewhere around there. And that's just going to be straight up. And then what? If we add more energy, what's going to happen?
The temperature will change.
Yeah, it's now a gas and the temperature is going to rise. So we would now be using the slope for gas instead, this value, 0.8625 as our slope. But we can still use the same sort of calculation for a gas. Delta E equals the new slope times the change in temperature. So that's 0.8625. And there isn't really a next temperature to use as a stopping point, but we can just choose any point we want. Let's say we jump from 125 to 175. So because we need to mark one more point in order to draw a straight line. So let's say we just raise the temperature by 50 Kelvin. 0.8625 times 50 would be 43. Times 10 to the negative 21 joules. So that means by the time we get to 175, not that anything special happens to 175, but just another convenient point on the graph, we'll be adding 43. So 209 plus 43 to the energy is going to be 252. Again, nothing special about that. Energy is just a convenient reference point to use. So 252 is going to be about here. And there's our next line. So that would be the entire graph then. And what sort of graph have we just created? What model is this? What does this look like from way back at the beginning of the quarter?
The three-phase model.
Yeah, this is just the three-phase model. We've swapped the axes. We've got energy and temperature instead of energy and temperature. But if you turn your head sideways, this is exactly the three-phase model we were working with at the very beginning of the quarter. This is where that graph comes from. Any other questions on that? All right, then I think that is about it. Have a good weekend, study up. Let me know if you have any other questions. And I will also have office hours Monday morning and Tuesday morning and afternoon. So good luck on finals, have a good break, and I hope to see you in 7B next quarter. Bye-bye.
Thank you.